Welcome to the first part of Lesson 2. In Lesson 2, we are going to focus our attention on the most fundamental types of organic molecules, specifically alkanes and cycloalkanes. Starting here will give us the chance to learn about the core structures of organic molecules, how they are named, and what types of shapes and forms they can adopt. In Part 1 of this lesson, we are going to focus on the structure and nomenclature for alkanes. We will begin by learning how hydrocarbons are classified. Next, we will delve into the concepts of isomerism and nomenclature, which will help us see the variety and complexity that occurs, even within the simplest organic compounds, and also give us the tools necessary to describe and name their structures. When we were first introduced to the concept of functional groups in Lesson 1, we learned that one class of molecules are the hydrocarbons. Hydrocarbons are organic molecules that contain only carbon and hydrogen atoms. In organic chemistry, hydrocarbons are divided into two classes: aromatic compounds and aliphatic compounds. Aromatic hydrocarbons are hydrocarbons that contain a benzene ring. Aliphatic hydrocarbons are hydrocarbons that do not contain a benzene ring. Aliphatic hydrocarbons can have single, double, or triple bonding present between the carbon atoms and their structures. The presence of these features, which we learned are called functional groups, change how we classify the substance, because these features have different physical and chemical properties. For example, when an aliphatic hydrocarbon has all single bonds between carbon atoms, it is called an alkane. Alkanes can be found as so-called open-chain type structures, or within ring-type structures. We use the name cycloalkane to refer to these cyclic versions of alkanes. Aliphatic hydrocarbons can also have carbon atoms that have double and triple bonds between them. Hydrocarbons with CC double bonds are called alkenes. Hydrocarbons with CC triple bonds are called alkynes. If these functional groups are found within rings, we would refer to them as cycloalkenes and cycloalkynes respectively. One of the first steps we need to take to better understand the structures of hydrocarbons is to learn the concept of branching and degree of substitution. If we look at the carbon atoms that make up the structure of a hydrocarbon, we see that each carbon in the structure is always bonded to at least one other carbon atom. It is also possible that a carbon may be bonded to more than one other carbon atom as well. We frequently describe and classify carbon atoms based on this observation. We describe this as the degree of substitution for a carbon atom. The degree of substitution refers to how many other carbon atoms a given carbon atom is directly connected to by a covalent bond. For example, when a carbon is bonded to one other carbon, we classify it as a primary carbon. If it is bonded to two other carbon atoms, we classify it as secondary. It follows that a tertiary carbon is bonded to three other carbon atoms, and a quaternary carbon is bonded to four other carbon atoms. Note here that secondary carbon atoms are often associated with the abbreviation sec, and tertiary carbon atoms with the abbreviation tert. Also note that we use the symbol for degree next to a number 1, 2, 3, or 4 as a shorthand description for primary, secondary, tertiary, and quaternary, respectively. If we were classifying the labeled carbon atoms C2, C3, C4, and C6 in the molecule shown below, we would see that C2 is bonded to four other carbon atoms, as I am indicating on the drawing, and therefore, we would classify this carbon as quaternary. Looking at the carbon C3, on the other hand, we can see that it is only connected to two other carbon atoms, and so we classify C3 as secondary. What is the degree of substitution for C4? That's right, C4 is connected to three other carbon atoms, and so C4 is a tertiary carbon. Finally, we get to C6. We can see that C6, which we also might refer to as a terminal carbon atom, because it is at the end of a chain, is only connected to one other carbon atom, and so C6 is classified as primary. A systematic way of naming chemical compounds, according to a set of rules, was established by an organization known as IUPAC, which is the International Union of Pure and Applied Chemistry. This system ensures that every compound has a unique and unambiguous name, facilitating communication among scientists globally. The IUPAC nomenclature covers various types of compounds, including organic, inorganic, and coordination compounds. We will be learning the basics of the IUPAC system in the context of organic compounds, and we will learn these basics by starting with alkanes. Once we learn the rules for alkane nomenclature, we can apply these rules to all other organic compounds, just by adding in new details about various functional groups. Our objective is to be able to look at the structure for an alkane, and provide its systematic name. Additionally, we will learn how to draw the structure for an organic compound, when we are provided with its name. The fundamental components of the name for an organic compound is comprised of the following key features. The parent chain. For organic compounds, the longest continuous chain of carbon atoms is identified as the parent chain. The parent chain is the core of the organic molecule, and the name of the parent chain is the core of the compound's name. Once the parent chain is identified and named, we need to include substituents that may or may not be present. Substituents are atoms or groups that are connected to the parent chain. We include substituents in the front part of the name, in what is called the prefix. In addition to the name of each substituent, their locations are specified as well. We will learn how to assign location numbers to our organic molecule in a systematic way, so that there is no ambiguity. These location numbers are important, as they are used for describing the location of substituents and other features of the molecule. We will also see that a critical feature of the name is included at the end, after the name of the parent chain, in what is described as the suffix. The suffix is reserved for specifying the highest priority functional group within the molecule. Each functional group has its own unique suffix that we include in the name. We will see, for example, that all alkanes have the ane suffix, whereas alkene have the suffix ene. The molecule 2-bromoheptane, for example, is an alkane, but the molecule 2-bromo-2-heptene is an alkene. Before we get into too many details, however, we need to start with the basics. Specifically, we need to learn how to identify the parent chain and how to assign it a valid name. From there, we will learn how to handle substituents and the suffix. Let's go to the next page and get started. The first step in naming an organic compound is to locate and name its parent chain. Here is the process. First, locate the longest continuous chain of carbon atoms in the structure. Because of branching, there may be multiple chains within the structure. Examine each branch and find the longest pathway through the branch, counting carbon atoms along the way. Once you have identified the longest chain in the structure, and counted how many carbon atoms are present in that chain, it is time to assign the parent name prefix that corresponds to the number of carbon atoms. Included here is a table that includes the name prefixes that correspond to parent chains with lengths of 1 through 10 carbon atoms. You will need to commit these correspondences to memory for recall later. Once you have assigned the correct parent name prefix, it is time to complete the parent name by attaching the suffix. For hydrocarbons, the suffix is also called the multiple bond index, or MBI for short. We need to choose the correct MBI, based on the presence of any multiple bonds in the compound. If the hydrocarbon only contains CC single bonds, for example, the suffix ane is used to designate the compound as an alkane. If there are CC single and CC double bonds present in the hydrocarbon, the suffix ene is assigned. Additionally, if the compound has any CC triple bonds, the suffix becomes yne. A hydrocarbon with both double and triple bonds would still be assigned the yne suffix. Let's try this process out with a few examples. In this first structure, we can see that there is a branching point at the carbon atom located here. If we examine the various chains of carbon atoms, by inspection we can see that the longest continuous chain is 5 carbons in length. This means we would use the prefix pent in our parent name. Now it is time to complete the parent name by assigning the MBI. We can see that the compound is an alkane, as it only contains CC single bonds, and so we use the ane suffix. Our parent name for this compound becomes pentane. Notice that we haven't dealt with the single carbon atom that is attached at C3 on the parent chain. That carbon atom is a substituent, and we will learn how to deal with substituents shortly. Let's try this process out again on the second example. Examining the structure, we see that the longest chain of carbon atoms is 5. We also see that the compound contains only CC single bonds. This example therefore also has the parent name of pentane. Finally, in our third example, we can see that the parent name is pentane as well, as the longest chain of carbon atoms is 5. One question you might ask yourself at this stage is, are these 3 examples the same compound or are they different? We will soon see that 2 of these compounds are identical, even though they are drawn differently on the page. All of the examples shown here have the same chemical formula, but there are 2 different compounds. These 2 compounds are isomers of each other, because they have a difference in the connectivity of atoms and their structure. You will learn that nomenclature is a great tool for helping you to quickly spot situations like this, and how to see the differences between identical compounds and their isomers. When analyzing a structure, you may find that there are 2 different chains of equal length. We can see an example of this in the structure shown below. Notice that the 2 different pathways I have indicated here on the structures have the same number of carbon atoms. 2 questions you might ask yourself at this point are, how do you determine which of the chains is the correct parent chain, if they have the same length? And, why does it matter? To answer the first question, we have to compare the number of substituents present on each of the candidate chains. The candidate with the greater number of substituents is elevated to the rank of parent chain, and the other is cast aside, never to be thought of again. To answer the second question, we have to look at the next step in the nomenclature process, which involves assigning location numbers to the parent chain. Even if 2 chains have the same length, they may have different substituents at different locations. As mentioned previously, substituents are atoms or groups of atoms that are attached at various locations along the parent chain. A complete name for a compound needs to include the location and identity of each substituent. We need to learn, A, how to specify substituent locations, and B, how to name substituents. Let's start with the location assignment first. To assign locations to substituents, we need to number each carbon atom in the parent chain sequentially, starting at 1, and continuing to the end of the chain. There is often more than one way that the numbering can be done, so we need to have a rule in place so that location numbers are assigned consistently. When numbering the parent chain, the goal is to assign the lowest possible numbers to any substituents. The correct numbering scheme will follow this rule. As an example, let's consider the structure of the molecule we were looking at on the previous page. I will draw it here again, twice actually, so we can compare different ways of numbering the structure and choose the correct version. I will start by assigning numbers along the chain. But notice that I can number the chain in two different ways. If I start numbering the parent chain on the left, and go sequentially to the right, my substituents, which are located here and here, are assigned location numbers of 2 and 3. If I start numbering from the other side, however, my substituents would get the location numbers of 4 and 5. So there are two possible ways to number the parent chain. Which one is correct, and how do we choose the correct numbering scheme? We use the numbering system that gives the lowest location number at the first point of difference. To understand how this rule works, let's look at a few hypothetical examples. Imagine we have two competing numbering schemes, one that has a 2 and a 3, and the other that has a 3 and a 4. We start by comparing the first column of location values, that is, the first locations that occur in the list. In this example, we are comparing between a value 2 and a value of 3. These two numbers are different, and so this is the so-called first point of difference. The numbering scheme that has the lower location value at this point is the better scheme, and that is the scheme that we use. Now that we know how to assign locations to substituents, we need to learn how to assign names to them as well. Hydrocarbon-based substituents that have all carbon-carbon single bonds are called alkyl groups. Alkyl groups are named based on the number of carbon atoms in the chain, using the same prefix names that we were introduced to when naming parent chains. We complete the name of an alkyl group by attaching the YL suffix. So, if we have a CH3 substituent, we use the meth prefix and the YL suffix to give the name methyl. If we have a 2-carbon substituent, with the formula CH2CH3, we use the name ethyl. Propyl is the name that we use for a 3-carbon alkyl substituent, and butyl is used for a 4-carbon substituent. Let's see if we can apply these rules and derive a name for each of the example structures shown here. First, let's find the parent chain for each molecule. Here in the first structure, we can see that the longest chain of carbon atoms follows the indicated pathway and has 5 total carbon atoms. The parent chain has 2 total substituents. We continue by assigning location numbers starting closest to the first substituent. We can now make a list of our substituents, including their names and locations. These are both 1-carbon alkyl substituents, and so they are both called methyl groups. We have a methyl group at carbon 2 and another at carbon 3. This is our substituent inventory, and the parent chain is pentane. We will learn shortly how to assemble these pieces into a complete name. Our second example structure has a 6-carbon parent chain. Since there are 2 6-carbon chain pathways available, we will choose the path that has the most substituents as we assign location numbers. There are 2 substituents, a methyl group at carbon 2 and an ethyl group at carbon 3. We will use these substituent names and locations, together with the parent name, which is hexane, to assemble a complete name for the molecule in a later part of this lesson. In both of these structures, we have seen examples of simple, unbranched alkyl group substituents. There are a few other types of alkyl substituents you need to be aware of before we learn how to assemble a complete name. When alkyl groups have 3 or more carbon atoms, it becomes possible for carbon atoms in the groups to be connected in different ways. This gives rise to the existence of alkyl group isomers, that is, alkyl groups with the same number of carbon and hydrogen atoms, but different structures. Because these structures are different, even though they are made from the same number and types of atoms, we need names to be able to differentiate between them. There are common names used for various alkyl group isomers, and we will learn the names for those that have 3 carbon atoms and 4 carbon atoms. You will need to be able to recognize these structures and identify them by name and vice versa. Let's start by looking at the names for the 3 carbon alkyl groups first. The first 3-carbon alkyl substituent we consider is called a propyl group. This 3-carbon alkyl substituent is attached to the parent molecule at one of its terminal carbon atoms. This is the so-called normal isomer, and sometimes you will see it written as N-propyl. The name N-propyl is used when we have attachment at C1 of a 3-carbon alkyl substituent. The other 3-carbon alkyl group substituent happens when the parent chain is connected at C2 of the propyl group, rather than C1. We still have a propyl group, but we must give it a different name, because it is structurally different. The name isopropyl is used. Consider the 2 example molecules shown below. These compounds were synthesized from the same starting material, with an N-propyl group attached at the sulfur in the molecule on the left, and an isopropyl group attached at the same location in the molecule on the right. The name for each compound is included, and we can see that the N-propyl and isopropyl group names, and their locations, are shown in red, as a part of the complete name for each compound. Now that we know the names and structures for the alkyl groups that have 3 carbon atoms, N-propyl and isopropyl, let's learn the names and structures for the alkyl isomers that have 4 carbon atoms. When an alkyl group has 4 carbon atoms, there are 4 total possible isomers. Each of these isomers is given a corresponding name that we will use. To make it easier to remember these structures and their names, it is very helpful to look at where these isomers come from. First, if we consider a 4-carbon parent chain connected without any branching, we get the molecule N-butane shown here. Butane is the parent of 2, out of the 4 total possible, alkyl substituents that have 4 carbons in their skeleton. Let's see how we can get 2 isomeric substituents from this single structure. First, when we connect a parent chain to one of the terminal atoms of this chain, we get the N-butyl group. But there is one other possible location where we could connect a parent chain to the N-butane structure. Do you see where? That's right. We can also connect at the second carbon in the chain. This is the alkyl group called sec-butyl. So from the normal unbranched 4-carbon chain, we can get 2 possible alkyl group isomers, N-butyl and sec-butyl, based on where the parent chain is attached. Where do the other 2 butyl isomers come from? To answer that question, consider that there is one additional way we can arrange the 4 carbon atoms in butane. Specifically, we can attach one of the 4 carbon atoms to the central carbon instead of the terminal carbon. This difference in connectivity creates a branched isomer of butane with the formal name of 2-methylpropane. The common name of this molecule is isobutane. Looking at isobutane, we can see that there are 2 unique attachment points. This is the origin of the 2 additional isomers. The first of the 2 attachment points is either of the terminal carbon atoms. As a substituent, this is called an isobutyl group. The other attachment point is at the central carbon atom. Notice that the central carbon atom is bonded to 3 other carbon atoms, making it tertiary. For this reason, we name this the tert-butyl group. So, in summary, we have 4 different alkyl groups that are possible when there are 4 carbon atoms in the substituent. There is the N-butyl and sec-butyl groups, which arise from attachment at carbon 1 or carbon 2 of the butane structure. We also have the isobutyl and tert-butyl groups, which are based on attachment to the isobutane isomer at one of the terminal carbon atoms, or the central carbon atom of that structure, respectively. Let's go to the next page and look at some examples. Shown below are several examples for the alkyl group isomers we have learned so far. Pause the video and see if you can identify the name for these alkyl groups, which are highlighted in red. Write your answers down in your notes, and then when you unpause the video, you can check your answers. All right. Now that you have had a chance to write your answers, here are the correct names. How did you do? If you missed any, take a look at the previous pages in the notes and re-watch those sections of the video and try again. Great work! Now that we have a good understanding for how to identify and name alkyl groups, let's go to the next page and learn how to put together a complete name for an alkane. Once the parent chain is identified, named, and numbered, and the substituent inventory is completed, we are ready to assemble a complete name for the compound. To do so, we will follow the format shown below, adhering to several rules as we assemble the name. We start the name by listing each substituent. To do this correctly, we will be listing our substituents in alphabetical order, using the first letter of the parent name of the substituent. Remember that the parent name is not based on structural prefixes, such as tert or sec. So a tert-butyl group would be alphabetized using the letter B, not T. When we list substituents, we will separate location numbers from letters, using the dash symbol. So dashes are used in between letters and numbers. When we need to separate multiple numbers from each other, we will use commas to do so. So commas are used in between numbers and other numbers. Note that we will always have a location number for every substituent. Finally, when we have multiple identical substituents, even if they are at different locations, we will combine those substituents together in our name, using numerical prefixes such as di, tri, tetra, etc., to indicate the number of times that substituent occurs in the structure. Let's apply these rules to the example shown here. We found earlier that the parent name for this structure is pentane, and we can number the parent chain as shown here. We see there are two substituents here, a methyl group at carbon 2 and another methyl group at carbon 3. To assemble the name, we will start by putting together the two identical methyl groups into a string that reads 2,3-, and then dimethyl. We then attach the parent name, pentane, to the end of this string, and we have the complete name for the structure. On this page and the following, there are a collection of examples for you to practice the ideas we have learned so far in the lesson. Start by pausing the video on this page and writing down the complete name for each structure, following the principles and rules we have learned. When you unpause the video, the solutions will be shown, one at a time, from left to right. Check each answer sequentially, one at a time, with the video paused. If you have an error on that problem, look to see if you can correct it on a subsequent problem, before unpausing the solution video. Now would be the time to pause the video and solve each problem. Finished? Great. Here are the solutions. Check each of your answers as they are shown. Let's now go to the next page. On this page you will try converting names into structures. As on the last page, pause the video and solve each problem by drawing the structure that corresponds to each name. When you unpause the video, the solutions will be revealed sequentially, one at a time. Check each of your answers and continue to the next page when you are ready. Did you check all your answers? Great. Let's go to the next page. As mentioned earlier, the other category of hydrocarbons are the cycloalkanes. A cycloalkane is a type of organic compound that consists of a ring of carbon atoms bonded together with single bonds. The general formula for cycloalkanes is C sub N H sub 2N, where N represents the number of carbon atoms in the ring. Compare this with acyclic alkanes, which have the formula C sub N H sub 2N plus 2, because they have 2 additional hydrogen atoms. Just as in acyclic alkanes, cycloalkanes are given a parent name based on the longest chain of carbon atoms in the ring, with the addition of the cyclo prefix, to differentiate them from acyclic alkanes. Examples of cycloalkanes include cyclopropane, cyclobutane, cyclopentane, cyclohexane, and so on. We can draw the line structures for these compounds as shown below. We can also name substituted cycloalkanes, in a similar way to how we named substituted acyclic alkanes. Numbering a cycloalkane depends on how many substituents are attached to the ring. When there is only one substituent on a cycloalkane, the carbon atom in the ring that is attached to the substituent is automatically assigned the location number 1. When we write the name of a mono-substituted cycloalkane, it is not necessary to include the number 1 before the name of the substituent, because there is no other possibility. Using this rule, we can name the following alkanes. We have a methyl cyclopentane, followed by an isopropyl cyclobutane, and finally, a sec-butyl cyclohexane. How do we number a cycloalkane that has 2 substituents? We start by assigning the location 1 to the carbon in the ring that has the alphabetically highest priority substituent. We then proceed to number in the direction to give the second group the lowest possible location value. Let's see how this works in the following examples. On the first example, we have a substituted cyclopentane molecule. Because there are 2 substituents, we need to identify which of the ring carbon atoms is assigned the location number 1. There is a methyl group and an ethyl group. The ethyl group has a higher alphabetical priority, and the carbon atom attached to this ethyl group is assigned as C1. We then proceed to the next carbon atom. Because we want the lowest number for the second substituent, we would number in the direction to give the carbon attached to the methyl group as C2, rather than going in the other direction, which would lead to a C5 assignment. So the name for this compound is 1-ethyl-3-methyl-cyclopentane. Notice that I do need to include the location number 1 for the ethyl group in the name here, because we have more than one substituent. On the next example, we also have a methyl and an ethyl group, but the location numbers are 1 and 3. The name is shown below the structure. On the last example, we have a cyclohexane with 2 substituents. To assign location values, we need to identify the names for each. One substituent is the tert-butyl group, which is alphabetized using the letter B. The other substituent is the 3-carbon isopropyl group, which is alphabetized using the letter I. Because the tert-butyl is higher priority, alphabetically, the ring carbon to which it is attached is assigned the location value of 1. This means the isopropyl is attached at carbon 4. The complete name for the compound is therefore 1-tert-butyl-4-isopropyl cyclohexane. Occasionally, we will see acyclic alkanes with chain lengths longer than the ring size of an attached cycloalkane. In these cases, we treat the cycloalkane as a substituent on the parent acyclic alkane. To do this, we name the ring substituent as a cycloalkyl group. Two examples are shown here. We will conclude this part of the lesson by learning about one additional type of substituent, specifically halogen atoms. The halogens are elements found in group 7 of the periodic table, and they are a common occurrence as substituents on various organic compounds. When alkanes have halogen atoms attached, we refer to these compounds as haloalkanes, and also alkyl halides. Halogen substituents are named by changing the -ine ending of the element name to O, to designate it as a substituent. We number the parent chain following the same rules we used previously, and we construct the name of the compound in the same way as well. 3 examples are shown below. In the first example, notice that the bromo substituent is assigned the location number 2, and the methyl group at 5. This is due to the higher alphabetical priority of bromo over methyl. That concludes this part of Lesson 2, the nomenclature of alkanes and cycloalkanes. In the second part of this lesson, we will look closely at the structures of alkanes and cycloalkanes, including a detailed look at isomers and their conformations.